Hey everybody, I want to share sort of a companion definite integral here. This is a definite integral that involves the independent variable x, also the floor of x, and also the fractional part as a product in the integrand of this definite integral. Now, we are living in the interval -1 to 0 for the purpose of some of these definitions here. And so it's pretty clear that in the interval, we can just put it right here. In the interval, we are living in the interval -1, 0, right? And so it's very clear that in this interval, for x contained in this interval, I'll just write it like this: for x, a member of this interval, the floor of x is certainly equal to -1, right? And that's any number in that interval. You know, for example, -3/4 would have a floor of -1, right? So that's kind of cool because that's exactly the limits of integration here. And so as far as this integration goes, we know that the floor of x is just a constant value, -1, okay? Now, how about this fractional piece? It's, you know, anybody can figure out what the fractional piece of any number is. Like, for example, the fractional part of 4/3 is 1/3, right? But we need something more analytic, more algebraic to actually perform this integration. And so in this particular interval, the fractional, this very same interval that we're talking about with the floor function, we would have that the fractional piece of x is actually equal to x plus 1. Now you can actually sketch this. It's really pretty easy to see, you know, and I can do that just briefly here. Okay, we'll call this -1 right here, right? So the fractional piece function just looks like that, okay? Or this is -1 and then this is 1 right up here. And so moving from left to right. Now you get some strange results, like for example, the fractional piece of -2/3, for example, is actually a positive number, which is weird, you know. I think that's Graham's definition. Okay, but so this is actually kind of counterintuitively, and I thought it was wrong when I first saw it, but the sawtooth function is what it is, and that's what the fractional piece function looks like. This is -1 right here, right? This is 1. And so you can see that -2/3 is down here on the low end where you would have about 1/3 right there. So that's crazy. Now, fortunately, we don't have to deal with that here. Just trust it, you know, but it is the truth and it is a convention that has its justifications. Not saying I don't claim to know. But anyway, we know that in this interval -1 to 0, we can replace this with x plus 1. All right, just like that, folks. Okay, so we have a very simple, it's kind of nice when you can just replace a variable part of an integrand with a constant, but that's the special behavior of the floor function. It always returns an integer, right? So let's hop along to the next screen here. All right, and all I'm going to do is just show you the results of what we just did. Okay, y'all, I replaced this integrand with exactly what I told you it was equal to over here on the other page, on the previous page. And the rest of this is very, very straightforward. You can factor that -1 out and find this represents the antiderivative right here. X³/3 plus x²/2 is the antiderivative. And I spared you the agony of watching me do the arithmetic here. If you evaluate this piece right here at 0, and then subtract from it what you get when you evaluate it at -1, you'll get +1/6. And actually, this has a neat geometric interpretation. It's a very skinny, tall triangle, actually. So that might be something to explore one of these days. But in the name of brevity, I'll go ahead and stop right here. I hope you guys enjoyed. Leave any comments or questions.